All right, hello, welcome to our video on series circuits. We're going to study two specific types of circuits. We've already kind of talked about electric current. You should know how a basic circuit works. We're now going to talk about the two types, one of which is called series circuits. The other one, called parallel circuit, is we're going to talk about in another video. Series circuits are the most simple type of circuit, okay? We've already built a couple of series circuits in the simulation so far. But the definition of a series circuit is to connect a battery to one or more resistors or lamps or anything else that uses up energy under one condition. The one condition is that there must be only one path for current to flow through in the circuit. You can't have multiple paths. You can't have wires branching off, some of the current going one way, some of the current going the other way. So here's a few examples of possible series circuits. Okay, we're going to use the circuit diagrams that we see in the reference table. Here's a battery. We're going to connect that via wires to a resistor. This is the most basic type of series circuit you can have. One battery, one resistor, wires connecting the two. You could also have something like this. You could have something where there's two resistors. That's also a series circuit. Notice that there's only one path for the current to go through. Current leaves this terminal of the battery, goes through resistor 1, goes through resistor number 2, goes back to the battery. I'm sure you know where we're going with this. You could really have as many resistors in series as you want, okay? So the word series here simply means that the current has to go through each resistor one after the other. Now look, there's no place for the current to escape. There's no alternate path for the current to get from here to here. It has to go through all three resistors. In any circuit, and so also in series circuits, there are three measurable things. You can measure the voltage. No, remember, this is voltage drop. It's the electric potential difference between 2 points. Usually it's between 2 points on opposite sides of some circuit element or some circuit component. So you can measure the voltage drop across, let's say, this resistor, or this resistor, or this resistor, or all three resistors as a whole, or even the voltage gain across the battery. Usually that's labeled for us, though. We could measure the current, the number of charges flowing in the circuit per second. We could also measure the resistance of any piece of the circuit, any circuit component. So the main rule guiding series circuits is this. There must be only one path for the current to flow through. Based on that, there are 5 kind of conclusions that we can come to. The first one should be familiar. The total voltage drop or gain. The sum of all the voltage drops at all the different pieces of the circuit where energy is dissipated, where energy is given off, across all resistors or lamps is equal to the voltage gain of the battery. And to symbolize that, we have this equation, and it is in the reference tables. There's a specific section under series circuits right here. We're looking at this second equation down right now. V equals V1 plus V2 plus V3 plus ... What V stands for, and I really like to write VT for V total, is the total voltage drop across the entire circuit. V1 plus V2 plus V3, each of those individually numbered V's is simply a voltage drop for a particular resistor or a particular lamp. Okay, and we've talked about that before. We've talked about how that works for a circuit. Okay, we talked about it in the last video. If we take a look at the simulation, we see that this is the case. We have a 9-volt battery powering this circuit. We have a voltmeter here. We have an ammeter here. We have two 10-ohm resistors. So if the voltage drop must equal the voltage gain, the total voltage drop must equal the voltage gain of the battery, we take a look at the voltage drop by connecting the probes across the first resistor. It says 4.5 volts. Notice it's always red goes before the resistor, black goes after the resistor. And we look at the other one. That also says 4.5 volts. We add 4.5 and 4.5 and we get 9. So that seems like it makes sense. Matter of fact, take a look at this. If we take a look at the voltage drop including both resistors, so we put this before the first resistor and the black one after the resistor, we get 9 volts for the total voltage drop. This will stay the same if we change this voltage. Let's bring this up to 40. We still see that the total voltage drop is 40. The voltage drop for the first one is 20. The voltage drop for the second one is 20. And the total voltage drop is 40 volts. This even works if we change the resistance of one of these. Let's make this, I don't know, 95, sure. Notice that the total voltage drop is still 40 volts. For this first one, the voltage drop is 36.19 volts. For this second resistor, the voltage drop is 3.81. Do some quick math in your head. 36.19 is basically 36. 3.81 is basically 4. Add those two together, 36 and 4, you get 40. Okay, so that rule works no matter what the individual resistances are, no matter what the total voltage is. The sum of the voltage drops in the circuit, in one path of the circuit, must equal the voltage gain of the battery. All right, rule number 2, the individual voltage drop of each resistor. Now we saw this when we started changing the resistances, that the individual voltage drops were the same. When the resistances were the same, the individual voltage drops were the same. When the resistances were different, the individual voltage drops were different. The individual voltage drop across a resistor is equal to, or a better phrase might be, can be calculated with this equation, V equals IR. This is known as Ohm's law. You've seen Ohm's law before, but not written like this. Ohm's law is simply this, the definition of resistance. I think you're more commonly going to see it written like this. And again, what this is it's the voltage drop across a circuit component is equal to the current through that component times the resistance of that component. Component just means a piece of a circuit, typically one that dissipates energy, that uses up energy, like a resistor or a lamp. Okay, let's see that this works. Let's go back to our simulation. All right, we see that the resistance of the, let's do the one on the right first, the 10 ohm resistor. It's a 10 ohm resistor. We see that the voltage drop for it is 3.81, and we also see, let's use our little current tool here, that the current is 0.38 amps. If I divide, let's see here. If I divide, let's see, so we got to do voltage divided by current to get the resistance. 3.81 divided by 0.38. Within some rounding, I get a resistance of 10. Let's try it for the other one. The voltage drop for this second resistor is 36.19. So I do 36.19 divided by the current of 0.38, and we get 95, and that is the resistance. This even works if I change, oh, and by the way, take a look at the current here. Notice that the current seems to be approximately the same everywhere, okay? It's always about 0.38. Doesn't change. That's really important. Matter of fact, okay, so let's do this. Let's change the resistance here. Make it 22. Notice that this seems to have changed the current. It's now 1.25. The voltage is, let's see if we can read this, 27.5. So let's do 27.5 divided by a current of 1.25. That gives us our resistance of 22. So we see that the individual voltage drop, the voltage there, is given by the product of the current times the resistance. Or, stated another way, the resistance of that piece is equal to the voltage drop divided by the current. And that is always true for these resistors in this circuit. Matter of fact, we could even do something like this. Actually, you know, I'm going to save that for one of the next points. Okay? But one of the things I also want you to notice is that the current is the same everywhere. Everywhere in the circuit. If I change the voltage, that's going to affect the current. But the current is still the same at all locations, given that you're not changing the circuit, changing the parts of the circuit itself. The current is the same at all locations. That's a really important piece for series circuits. That's one of the main rules. Matter of fact, it's in the reference tables. Right here it says the current equals the current at resistor 1 equals the current at resistor 2 equals the current at resistor 3. The current at all points in a series circuit is the same. That doesn't mean every series circuit has the same current at all points. It just means in a given series circuit, as long as the voltage and the resistances aren't changing, the current will be the same at all points. Okay. So number 4, going back to what we were just going to talk about a second ago, individual resistors. For any resistor, the ratio R equals VI, the definition of the resistance, is a set number that does not change no matter how much current goes through that resistor. Because of this, we say that resistors follow Ohm's law. It actually turns out if you go into higher branches of electrical circuit analysis and you do this at a higher level, that this law doesn't always necessarily hold for everything you could put in a circuit. It holds for a lot of stuff and it holds for the basics, but it doesn't always hold. Everything that we're going to look at this year is going to involve things that follow Ohm's law. The adjective for things that follow Ohm's law is to say that they are ohmic, O-H-M-I-C. Ohm is the guy who kind of came up with this rule, who studied this and found this out. All right, back to the simulation. We see that R for this resistor is 22 ohms. We see that the voltage right now, what did we say? It's 37.81 divided by the current of 1.72. That gives us about 22 ohms. If we turn up the voltage of the battery, if we increase the voltage of the battery, notice that the voltage drop here is going to change. Changing the battery voltage, basically meaning there's more power or energy to be given off in the circuit, is going to change how much energy is given off here. It's also going to change the current. And I'm going to get rid of this. I'm going to show how we actually measure the current. We actually usually will have an ammeter like this. It has to be wired directly into the circuit like so. Like this. Okay? So see that ammeter, it's reading the exact same thing as this little cheating thing over here. You can't just hover over a wire and find the current normally. And just to show you again, before I get back to my point, that ammeter can be connected at any location. Matter of fact, I'll bring it all the way down here and connect it. And it'll still read the same thing. Okay? So that current is 1.72 amps. Now, if I were to change the voltage of the circuit, I'm going to bring it down, that's also going to change the current. If I decrease the voltage, it should decrease the current due to Ohm's law. I'm not changing either of these resistances. Let's bring it down to like 30. There we go. Notice that the current went down. It kind of looks like the arrows are moving a little slower. The speed of the current doesn't really tell you the speed of the electrons, it just tells you how many electrons there are. So don't get fooled into thinking that they're like moving faster or anything when there's more current. It usually just means that there's more of them. Well, anyways, we still want to find the voltage drop. We want to see if this is actually ohmic. We want to see if the quotient, if when we divide the voltage by the current, we get the same number for the resistance. So we do 20.62 divided by 0.94. We get approximately 22. We once again see that this is ohmic, okay? Any errors are just due to rounding because this doesn't go out to very many decimal places. So what we're seeing right now is that the resistors in this simulation follow Ohm's law, okay? The resistance of each of them is simply a number. It's the ratio of the voltage drop across them to the current. If there's a bigger voltage drop, there should be a bigger current, but the resistance for each individual piece should stay the same, unless I click on the resistance and change it manually. Okay? Last thing that we're going to do is we need to talk about the equivalent resistance. Equivalent resistance really means like the resistance of the entire circuit as if we were just combining it into one big overall circuit. The total resistance of a series circuit is given by the following equation, which once again is in the reference tables. Req for equivalent resistance equals, for a series circuit, R1 plus R2 plus R3 plus dot dot dot. So what that says is for a series circuit where there is only one path for the current to flow through, to get the total resistance of the circuit, all you have to do is add up the individual resistances of the resistors. That's literally all that you have to do. One of the nice things about Ohm's law is that it applies to circuit components. It can also be applied across the entire circuit. So we could take this equation, and it's nimble. It's useful in a lot of different places. We could say that we can apply it across the entire circuit by saying the voltage gain from the battery equals the current in the circuit, since the current's the same everywhere, times the equivalent resistance. We don't have to look at just individual resistors. We could look at the circuit as a whole. Voltage gain for the entire circuit equals current in the circuit times the equivalent resistance. Let's see that here. We know that the voltage gain for the battery is 30, which, let's just double check, that means the voltage drop across both resistors is 30 volts. And we see that the current is 0.94 amps. So, Ohm's law, V equals IR, tells me that the equivalent resistance I could find by taking the voltage gain for the circuit dividing by the current. That would be 30 divided by 0.94. 30 divided by 0.94 is equal to 31.91, very close to 32, and take a look at my two resistors, 22 and 10. Add those together, R1 plus R2, I get 32. That's going to be the same if I change the voltage. Let's bring it all the way up. Let's make it 120 volts. If I do 120, that's the new voltage gain of the circuit, divided by 3.75, that's the current, I get 32. Guess what? The equivalent resistance of the circuit is still 32. Matter of fact, this works even if I add in a new resistor. Let's bring a new resistor in here. Let's make this resistor, I don't know, let's make it like 104, sure. Okay. So now we have a voltage gain for the battery of 120 volts divided by a current of 0.88. We have an equivalent resistance of 136.36, about 136 or so. 22 plus 10 plus 104. Guess what? It's 136. It works out. Okay? So the equivalent resistance can be found two different ways. Using the voltage gain for the battery, or in other words, the voltage drop for the entire circuit, divided by the current can equal the equivalent resistance, or we just add up the resistance of all of our resistors. Let's get to some examples. In this first example, we have a voltage drop of 6 volts, a current of 0.02 amps. We want to know the resistance. Well, Ohm's law tells us that the resistance, Ohm's law tells us that the voltage drop for this part of the circuit must be equal to the current times the resistance. So here's what we can do. We can say, let's see, the voltage drop we know is 6 volts. The current is 0.02. We multiply it by R, and we find out that R is 300 ohms. Remember, the symbol for resistance is this funny little horseshoe shape. That's a Greek letter, capital omega. That's for ohms. Let's use a simulation to check this. Now, because we had 6 volts and we had a resistance of 300 ohms, the resistors on here, you can't bring them up to 300 ohms. The most you can do, I think, is 120. Anyways, let's bring that back down to 30. Oh. Can't get it. There. Fine. There we go. Okay. So we bring this back down to 30. So what I've done is I have just cut the voltage by 10, I divide the voltage by 10, so it's 0.6. I divide the resistance by 10, so it's 30. That means if we divide V by 10 and R by 10, I divide both sides by 10, I should get a current of 0.2. Okay, notice I've divided both those by 10. I get the current, I'm going to use the cheating ammeter, of 0.2, so this works out. Let's take a look at the next example. Current of 0.005 amps, resistance of 700 ohms. We want to know what the voltage drop across this is. Ohm's law tells us that that voltage drop is going to be equal to the current through the component divided or multiplied by the resistance of that component. 0.005 amps multiplied by 700 ohms the voltage drop is 3.5 and the units are volts. Okay, that's telling us approximately how much energy is lost per unit of charge that passes through, 3.5 joules per coulomb. Again, here, I'm going to do a little bit of a trickery because I don't have a resistor of 700 ohms. So what I'm going to do is I'm going to keep the voltage the same. I'm going to divide 700 by 10. So that'll be 70. And what that should do is if the voltage is the same, but I divide R by 10, I should go up by a factor of 10. So I'm expecting 0.05 for the current. There's my voltage. There's my... There we go. So there's the voltage. There's my resistance. 0.05, exactly what I expect. Last example. Come on. Let's find the equivalent resistance of this set of resistors. Equivalent resistance, we know, and yes, you do have to write this formula, even though it's very simple and you're just adding things together, is given by this formula, R1 plus R2 plus R3. Okay? You don't have to write dot, dot, dot because you only have 3 resistors to deal with. So Req must be equal to 20 ohms plus 40 ohms plus 60 ohms. The equivalent resistance is, let's see, 20 plus 40, let's just do it here, 60 plus another 60, 120 ohms. So, if the equivalent resistance of this section is 120 ohms and the voltage drop is 6 volts, what is the current? We go back to Ohm's law. You see how useful this equation is. We know the voltage drop across the whole thing is 6 volts. Not individually 6 volts, but across the entire thing is 6 volts. The current is what we're looking for. The equivalent resistance, so I'm going to do Req and Vt, equals 120 ohms. I must be 0.05. So, we have this circuit assembled. We see that the battery voltage is 6 volts. Notice that individually, none of the voltage drops, so that one's 1. Individually, none of the voltage drops are equal to 6. This one is 2. And across this one is 3. But add them all together, 1 plus 2 plus 3, I get a total voltage drop of 6 volts. So the equivalent resistance, 20, 40, 60, it's 120. Let's confirm that. And the battery voltage is 6. The current is, where is it? 0.05 amps. Okay, so that's very useful and interesting that this equation works so well in describing all these different types of circuits. 0.05 amps. The rules for series circuits are really quite straightforward. They're very, very basic. What we're going to focus on is how to analyze a circuit from scratch. Like just be given a circuit, be given a few resistances or currents, and then figuring out everything else that there is to know about the series circuit. Okay? I will be back for one more video. We'll do 2 examples on the back, and then we'll be all set.